We ended the last part of this series calling this impact an opportunity. That might sound strange. A 4-ton piece of dead hardware slamming into the moon at nearly 9,000 kilometers an hour doesn't obviously sound like good news for anyone. But here's the thing that makes this event genuinely unusual from a scientist's point of view. Every year, the moon gets struck by natural material, rocks and debris from space, arriving with no warning, no known composition, and no known speed. When researchers study those craters afterward, they're essentially working backward from a mystery. A hole exists. They have to guess what made it. This impact was the opposite of that. Researchers didn't have to guess the mass. They knew it, roughly 4 metric tons. They didn't have to guess the speed. They knew it, 2.43 kilometers per second. They knew what the object was built from. They knew, almost to the minute, when it would arrive, and roughly where. For the first time in a long time, scientists got to watch a lunar impact happen with almost every variable already filled in. That's not a disaster. In a research sense, that's closer to a gift. So what actually happens physically when something like this hits the moon? And how is it different from the kind of impact the moon usually experiences? Here's where it gets genuinely interesting. A natural meteoroid typically strikes at incredible speed, often somewhere between 15 and over 70 kilometers per second. At those speeds, the impactor is usually dense, solid rock or metal. The collision is violent enough to instantly vaporize both the impactor and a chunk of the surface it hits, producing a flash of superheated plasma and a deep, roughly symmetrical crater. 2025-010D hit at about 2.43 kilometers per second. Still extremely fast by any everyday standard, but in impact physics terms, a much gentler regime than a natural strike. And it wasn't a dense, solid object either. It was a hollow cylinder, mostly empty space, wrapped in a relatively thin metal shell. Think about the difference between throwing a solid steel ball at a wall and throwing an empty aluminum can at the same wall, at the same speed. The steel ball transfers nearly all of its energy directly into the wall on impact. The empty can, on the other hand, crumples. A meaningful chunk of its kinetic energy gets absorbed just folding the can's own structure inward, rather than punching straight into whatever it hits. That's roughly what happened here, at a much larger scale. As the upper stage struck the surface, its thin-walled structure crumpled rapidly, within milliseconds, absorbing a portion of the impact energy in that mechanical deformation, rather than transmitting all of it directly into the lunar regolith below. The result? Instead of a deep, symmetrical crater punched out by a solid object, researchers got something shallower, with a less tidy, somewhat asymmetric spread of ejected material, and no dramatic thermal flash, just a comparatively low-temperature vapor plume. Same basic laws of physics as a meteoroid strike. A genuinely different outcome, because the shape and structure of the object mattered as much as its speed. And that outcome didn't just leave a crater behind. It threw material outward too, which brings us to the plume. When the stage struck the surface, it lofted a cloud of fine lunar dust and debris, what scientists call ejecta, upward and outward, reaching an altitude of several kilometers or more above the surface before beginning to settle. Some of that material almost certainly fell back down nearby, adding a thin new layer to the surrounding terrain. But here's a genuinely open question researchers are still working through. How much of the very finest, fastest-moving dust escaped the moon's gravity entirely, drifting off to join the thin cloud of microdebris that already exists in the space around the Earth-Moon system? Nobody has a confirmed answer to that yet. It's one of the loose threads this event left behind. And it matters more than it might sound, because that same question becomes a lot more important once you're talking about spacecraft and astronauts operating near the lunar surface. We'll come back to that. There's a partial clue, at least. A research team in Spain, working with a ground-based telescope, reported capturing preliminary video of material being thrown off the surface right around the predicted moment of impact. It's a single, not yet independently verified observation. Worth mentioning, not worth treating as settled. But if it holds up under scrutiny, it's one more angle on exactly how far and how fast that debris cloud actually moved. We already talked about the chemical signature this impact left behind: sodium and lithium, detected by telescopes on Earth, confirming both that an impact had occurred and, specifically, what kind of object caused it. But that same reading did double duty. It wasn't only proof, it was data. The sodium detected in that plume came from the lunar soil itself, vaporized by the force of the impact. Every time researchers get a clean reading like that, it adds to a broader picture of what the moon's surface is actually made of, in that specific region. A small but genuine contribution to lunar surface science, essentially for free, generated by an accident nobody planned. There's another kind of science this event connects to, one this series hasn't touched yet. What impacts like this can tell researchers about the moon's interior, not just its surface? This isn't a new idea. During the Apollo missions in the early 1970s, NASA astronauts left seismometers on the lunar surface, sensitive instruments designed to detect the moon's equivalent of earthquakes, known as moonquakes. And mission planners actually took advantage of leftover hardware to help generate signals for those instruments. Spent rocket stages and lunar module ascent stages were deliberately crashed into the moon after their missions ended, specifically so the seismometers could record the resulting vibrations traveling through the lunar interior. Those deliberate impacts helped scientists build some of the earliest real models of what's actually underneath the moon's surface. Its layers, its structure, how energy moves through it. Here's the catch with 2025-010D. There was no equivalent listening network in place to hear it. The Apollo-era seismometers were switched off decades ago, and there's no comparable active seismic array on the moon today. Researchers did model in advance roughly what kind of seismic signal an impact like this should theoretically produce. But without instruments on the ground actually listening, that stayed a modeled prediction rather than a captured reading. Which is a genuinely interesting kind of missed opportunity. We generated a large, well-documented lunar impact, the kind of clean, known event scientists specifically used to love in the Apollo era. And this time, nobody was in position to listen to what it might have told us about the moon's insides. So, put all of that together, and a clear theme starts to emerge. This impact gave researchers a rare, cleanly documented test case for crater formation, for ejecta behavior, for surface chemistry. And it also revealed a gap. The tools that could have captured even more from it, like a modern seismic network, simply aren't there yet. Neither of those facts is really about this one impact. They're about what's coming next. Because impacts like this one aren't going to stay rare curiosities. As more countries and companies send hardware to the moon, landers, orbiters, rovers, eventually crewed missions, the rate of human-made objects ending up on or near the lunar surface, whether intentionally or by accident, is only going to increase. That's part of why researchers were so eager to study this specific event closely. Teams working with detailed impact physics simulations, including a Los Alamos National Laboratory model called HOSS, built specifically to predict how objects like this deform and excavate material on impact, now have a real documented case to test those models against. Compare what a simulation predicted beforehand to what Denuri and the telescopes actually recorded afterward, and you find out exactly where your model is right and exactly where it needs correcting. That matters for reasons well beyond scientific curiosity. As more landers attempt touchdowns on the moon, and eventually as astronauts return to the surface under NASA's Artemis program and other national efforts, understanding how debris, ejecta, and impact hazards actually behave becomes a real, practical safety question, not just an academic one. Which brings us to the real theme of this part. There's a version of this story where 2025-010D is just an embarrassing mess, space debris, dead weight, an accident that happened to end up somewhere visible. That version isn't wrong, exactly. It's just incomplete. Because the more accurate version is this. An object nobody wanted, moving on a path nobody chose, happened to land in a way that scientists could actually learn something real from. That's not a coincidence born of luck alone. It's a coincidence born of tracking. If Bill Gray and the wider tracking community hadn't spent months refining exactly where and when this was going to happen, none of the telescopes would have been pointed the right way, and Denuri wouldn't have repositioned itself to catch the before and after images. The science only happened because the tracking made it possible to prepare. An accident became an experiment the moment people decided to treat it like one. And that idea, that an unplanned event can still be turned into something useful if you're paying enough attention and prepared enough to catch it, is about to matter a lot more than it does right now. Because this was one rocket stage, one impact, one well-documented event out of what is, historically, still a fairly quiet period around the moon. That period isn't going to last. Commercial landers are already flying regularly. National space agencies are ramping up lunar programs. Communications relays, navigation systems, and long-term lunar infrastructure are all being planned right now, not decades from now. Which raises a much bigger question than anything we've covered so far. If one accidental impact from one company's leftover hardware could generate this much genuine scientific value, and also expose a real gap in how we track and study events on the moon, what happens when there isn't just one piece of leftover hardware out there? What happens when there are dozens, then hundreds? The honest answer is, we're about to find out. Not in some distant speculative future, within the next few years. Because for most of history, the moon has been an occasional destination. A handful of missions, spaced years or even decades apart. That era is ending. Here's what occasional actually turned into. In 2025, 2 commercial landers touched down on the moon, one from Firefly Aerospace, one from Intuitive Machines. By 2026, NASA had moved well past treating any of this as a one-off. And that's just the beginning of the ramp-up. In 2026, NASA Administrator Jared Isaacman announced a goal of landing missions at the lunar South Pole on a monthly cadence starting in 2027. That's the stated ambition, not yet a guaranteed outcome. But behind it sits something more concrete. NASA's moon-based program has already awarded contracts to multiple companies, with Phase 1, running from now through 2029, targeting as many as 25 separate missions, including 21 actual lunar landings. Not all of those have flown yet. Most haven't. But the contracts, the companies, and the target dates are real commitments already in motion, not just a projection. Numbers that would have sounded like science fiction a decade earlier. And that's not a distant, speculative projection. It's the plan NASA is already under contract with private companies to build toward, right now. Compare that to the Apollo era, when a lunar mission was a national event, planned years in advance, one at a time. We're moving from a handful of missions per decade to something closer to several missions per year, and climbing. So who exactly is behind all of this activity? The honest answer is, a lot of different organizations, moving at the same time. Intuitive Machines has multiple missions in its pipeline, aiming for sites like the Reiner Gamma Magnetic Anomaly. Firefly Aerospace, the same company behind Blue Ghost Mission 1, has a second lander planned for the lunar far side, one that will need its own dedicated communications relay satellite, since the far side can't talk directly to Earth. Draper Laboratory, working with iSpace's American operations, has its own lander planned for the Schrödinger Basin, near the lunar South Pole. Astrobotic is preparing another attempt after its first mission never made it to the surface at all. And Blue Origin has its own cargo lander in development. Here's the part that matters for this story, though. Not all of these missions succeed. Astrobotic's first lunar attempt suffered a propellant leak and never reached the moon at all. It fell back to Earth days after launch. One Intuitive Machines lander landed, but tipped over on touchdown. And as we already covered earlier in this series, iSpace's Resilience lander lost contact during its own landing attempt, the same rocket launch that eventually produced 2025-010D. Every one of those outcomes, successful, partial, or failed, leaves something behind. A working lander, a tipped-over lander, debris from a failed landing, or, like 2025-010D, a piece of leftover launch hardware still drifting through space. More missions doesn't just mean more successes, it means more leftover hardware, full stop, regardless of how any individual mission turns out. And landers are only part of the picture. A lot of this activity never touches the surface at all. The European Space Agency's Lunar Pathfinder, for instance, is being deployed specifically to relay communications for far-side missions, since, again, the far side can't transmit directly to Earth. Firefly's own transfer vehicle, Elytra, is designed to ferry payloads and provide communications support in lunar orbit. South Korea's Danuri, which we talked about extensively earlier in this series, is still up there too, along with NASA's long-running Lunar Reconnaissance Orbiter. So the space around the Moon isn't just gaining new landers. It's gaining new orbiters, new relay satellites, new transfer vehicles, an entire layer of infrastructure being built up in the space between Earth and the lunar surface. Which brings us to the uncomfortable question underneath all of this. If a single successful mission can still leave behind an inert, uncontrolled rocket stage, like the one this entire series has been about, what happens as the number of missions climbs from a couple a year to nearly one a month? 2025-010D wasn't a freak occurrence. It was, in a very real sense, a preview. A lander that never reaches the surface leaves debris on a ballistic path back toward Earth or scattered elsewhere. A lander that tips over stays exactly where it fell, permanently. A spent transfer stage, once its job is done, becomes exactly the kind of inert, drifting object we spent the earlier parts of this series explaining in detail. None of this makes any single company reckless. It's simply what happens, mathematically, when you multiply occasional missions by a much larger number. More attempts, more outcomes, more leftover hardware scattered across lunar orbit and the lunar surface, which raises an obvious follow-up question. Who's actually keeping track of all of it? This is where things get genuinely difficult, for reasons this series has already touched on. We talked earlier about why 2025-010D was so hard to track using conventional methods, how objects at lunar distance are essentially invisible to the radar networks built to watch satellites closer to Earth. That problem doesn't go away as traffic increases. If anything, it gets more urgent. There are early efforts underway to close that gap. The U.S. Air Force Research Laboratory has been developing something called the Cislunar Highway Patrol System, a project specifically built to improve the ability to track and identify artificial objects operating at lunar distances and beyond. Researchers at Johns Hopkins Applied Physics Laboratory have also demonstrated new tracking techniques, using large radio antennas to pick up spacecraft signals across the vast distance to the Moon in ways traditional radar simply can't. These are genuinely promising steps. But it's worth being clear-eyed about where they stand. This is still early-stage experimental infrastructure, not a mature, comprehensive tracking network. One expert working in this field described current cislunar traffic as still resembling a quiet country road, with the clear expectation that it won't stay quiet for long. One industry estimate puts the current market for this kind of cislunar tracking and space situational awareness infrastructure at somewhere around $3 billion, projected to roughly triple within the next decade. Take the exact figure with a grain of salt. It's one analyst's projection, not a settled number. But the direction it points is hard to miss. This has stopped being a niche research problem. It's shaping up to be its own industry. So why does closing that tracking gap actually matter, beyond simple bookkeeping? Because the same physics that made 2025-010D so hard to predict cleanly, the three-body pull of Earth, Moon, and Sun, working together in ways that resist simple prediction, applies to every other object out there too. Many of the orbits used around the Moon are inherently unstable over long time frames, meaning objects don't necessarily stay where you'd expect them to, without regular correction. As more landers, orbiters, and relay satellites operate in the same limited region of space, that instability starts to matter in a very practical way. Two active spacecraft on unstable paths can, in principle, end up on a collision course with each other, the kind of event space agencies call a conjunction, and one that's far harder to predict and avoid out here than it is for satellites orbiting Earth. And 2025-010D already showed us what happens on the more passive end of that spectrum. An inert object, tracked for a year and a half, ending up exactly where gravity decided to take it. Multiply that by dozens of objects, some active, some dead, some drifting on unstable paths nobody's actively correcting, and you start to see the shape of a genuine navigation and safety problem, not just a tracking inconvenience. Which brings this part to its central point. Think about what it took to make driving on a busy highway reasonably safe. Lane markings, traffic signals, speed limits, radar and cameras watching for problems. None of that existed when there were only a handful of cars on the road. It became necessary specifically because traffic increased. Cislunar space is heading toward its own version of that same transition. Right now, the traffic infrastructure around the Moon is closer to where road safety was in the earliest days of the automobile. A scattering of early tracking experiments, some promising new techniques, and a lot of open space where nobody is watching closely yet. That's the real lesson underneath 2025-010D, not SpaceX left a rocket stage in space. Every launch provider currently sending hardware toward the Moon does something functionally similar, within the rules that exist today. The actual story is that we're entering an era where the number of objects around the Moon is about to grow faster than our ability to track, predict, and manage them. Put simply, the Moon is moving from a destination into an operating environment. 2025-010D is a prototype, a small, relatively low-stakes preview of a problem that gets meaningfully harder to ignore with every additional lander, every additional orbiter, every additional mission that doesn't go exactly according to plan. Which leaves one obvious question sitting on the table, and it's not a technical one. If cislunar space is about to get this much busier, and today's tracking infrastructure is still this early stage, who is actually in charge of managing it? Not, who built the rocket that caused this one impact? That question already has an answer, and it isn't a particularly dramatic one. The real question is, as more countries, more companies, and more competing interests start operating in the same limited region of space around the Moon, who decides the rules? Who enforces them? And what happens when nobody clearly does? Onward to Part 4. Follow the channel so it's there when it lands. No recap needed. It picks up exactly where this leaves off.